This lesson shows you how to relate and apply the Nernst equation at equilibrium conditions to relate the standard cell potential difference, the standard Gibbs free energy change, and the equilibrium constant for a given reaction. From the Nernst equation at equilibrium, we see the relationship that the standard cell potential difference equals the constants RT over F, and we have N, the number of moles of electrons per mole of reaction in the denominator, times the natural log of the equilibrium constant. Most of these questions are for conditions at 298 Kelvin, so with the temperature locked in at 298, RT over F just becomes the number 0.0257 with the appropriate units, and if you want to use log base 10 instead of natural log, mathematically the 0.0257 just becomes 0.0592, and that's just the relationship between log base 10 and natural log, or log base E. And again, the Faraday is a constant. It's the amount of charge per mole of electrons, which you can just get by proportion. The charge per one electron will yield quite a large amount of charge per mole of electrons, 96,485 coulombs per Avogadro's number of electrons. Generally 3 sig figs are used for that. So with R as a constant, the temperature at 298 Kelvin a constant, and F a constant, the only variable is N, the number of moles of electrons per mole of reaction, which you could see from the Nernst graph for a given electrochemical cell. The slope of the line is going to be equal to negative RT over NF, and at 298 K, that's just going to be negative 0.0257 divided by N. So empirically you could solve for N just by dividing negative 0.0257 by the slope of the line. Or in this case, where they actually plotted the E cell versus the log base 10 of Q, the moles of electrons exchanged per mole of reaction would use the negative 0.0592 divided by the slope. So once you have the standard cell potential difference for a given reaction, you can relate that to the equilibrium constant value or to the standard Gibbs free energy change, and if it's at 298 Kelvin, the numbers become simpler with those constants. So here's an example of that applied to the aluminum air battery. The oxygen in the air is the substance that's going to react with the aluminum. So as you just saw, the main variable we're interested in obtaining initially is N, the moles of electrons transferred per mole of reaction. We'll look at this reaction at 298 Kelvin so that the numbers will simplify. For the aluminum, naturally aluminum atoms cannot gain electrons from oxygen and form aluminum anions. So though this reaction is not on the AP table of standard reduction potentials, this can be searched through Google, and you see that tetrahydroxoaluminate 3 anion can be reduced to aluminum, and here's the value that you get from that. And for oxygen, the reduction generates hydroxide, and you see the quoted standard cell potential, and that is available on your AP tables. So between these two reductions as written, you could see from the positive and negative value that oxygen tends to be reduced, whereas the aluminum tends to be oxidized. So we'll have to rewrite the aluminum equation as an oxidation potential, which we do just by flipping the equation and the sign of the standard reduction potential to make it a standard oxidation potential. So as you can see with that done, now it's just a matter of balancing the electrons gained with the electrons lost, or vice versa. the oxygen line, I guess you had a sneak preview. We multiply by 3 to have 12 moles of electrons gained per mole of reaction there. And so we're going to have to multiply the aluminum line by 4. So that most important step yields N equals 4 times 3, or 12 moles of electrons per mole of reaction, as we're going to write in the balanced equation. So bringing everything down to get the net reaction, and correcting that little, I missed a sign there, on the aluminum anion species, we see that there are 16 hydroxides on the reactant side, 12 on the product, so we can completely eliminate the 12 hydroxides from the product side, and we end up with net 4 aqueous hydroxide on the reactant side. And then we do a quick charge check. On the left side, the total charge is -4, and on the right side, the total charge is also -4, so that indicates that things are working out correctly. But looking at the mass, forgot to bring down the water, so that's 3 times 2 H2Os. That would be 6 moles of water per mole of reaction written, and then the charge and mass should balance out. Those multipliers do not affect these ratios. Remember, a volt is a joule of work or energy per coulomb of charge of electrons exchanged in the reaction. So we just add those terms as written. So that's going to give us a standard cell potential difference of 2.73 volts. So writing that once more, a little bit cleaned up, we have the standard cell potential difference and the all-important N equals 12 moles of electrons per mole of reaction as written. That E cell standard is a relatively very large value, as you'll now see when we figure out the delta G standard for the reaction and the equilibrium constant, which you might expect for a metal aluminum and a non-metal oxygen, especially such a great oxidizer, would be quite product favored. Also notice that for these types of cells or batteries you would need basic conditions. This reaction would not go under acidic conditions. So let's get the standard Gibbs free energy change for this reaction as written. It's just going to be -N times the Faraday times E cell standard. Plugging in the values with units, 12 for N, the Faraday unit, and the E standard cell, we get a delta G standard for the reaction of -3,161,340 joules per mole of reaction, which to 3 sig figs works out to be -3.16 million joules per mole of reaction. And the trivial conversion to kilojoules will put it into less scary numbers. But the point is, you could see for a pretty small looking cell potential difference, 2.73 volts, in terms of useful work that could be produced by such a reaction. Delta G standard for standard conditions, that's going to be the negative of the maximum amount of useful work that could be extracted from that reaction, and so that's quite a bit for that battery per mole of reaction. And what is a mole of reaction here? 3 moles of oxygen. Oxygen is 32 grams per mole, so about 100 grams of oxygen consumed by the aluminum could get you over around 3.2 million joules of work from that battery or cell. So for such a large magnitude, negative delta G standard or delta G standard, we expect very heavily product favored equilibrium constant for standard conditions. So here's that calculation with units. We get a ridiculously large number. e to the 1277th power. You can see all the units in the exponent cancel, and if you have a TI-89 you can get this in base 10. I don't, so it works out to be about 10 to the 554th power, which again is just absurdly large and product favored. More importantly, it's good to know some general estimates or benchmarks. When you have a standard cell potential difference of around 0.10 volts, that's going to give you a delta G standard that's negative naturally, both indicating spontaneous standard processes or reactions. So the 0.10 in volts converts under standard conditions to negative 10 kilojoules per mole of reaction, and an equilibrium constant value of about 60, or heavily product favored. So even if you can construct a standard voltaic cell that has what seems to be a very little or low potential difference of 0.10 volts, you're going to get a very large K value and quite a bit of work per mole of reaction. Negative 10 kilojoules is the standard Gibbs free energy change. On the other hand, for the negative standard cell potential difference, that would not be a spontaneous or voltaic cell. A constant input of energy would be required to get that to run, 10 kilojoules per mole of reaction, just barely produced, and that would give you a heavily reactant favored equilibrium constant under those conditions of about 0.020. So it's good to keep in mind those benchmarks or numbers. So to summarize, for a given reaction at a given temperature, delta G standard, the equilibrium constant value K, and the cell potential difference standard, E0 cell, and the maximum amount of work that you can extract from that reaction are all interrelated and are all constant. In the notes I'll put an additional example of a galvanic cell, voltaic cell, another metal-nonmetal cell, so you'd expect a spontaneous reaction with a pretty large standard cell potential difference, and you can work through that and look up your answer in the notes.